Oh, here we go, everybody. Thank you for your patience with us. And hopefully you're having a great conference. My name is Mike Riley. I'm just playing your host and slideshow guy. But I'm introducing Anupam Goli, who is from 1746 over at Central Gwinnett, who is going to be talking to you about making your robot more intelligent with sensors. So with that, I'll give you Anupam.
Hey, so like Mike said, my name is Anupam Goli. I'm a engineering teacher and computer science teacher at Forsyth Central High School and the head coach of Team Auto 1746. It's a little bit about me, I guess. I graduated from Georgia Tech in 2016 with a degree in computer engineering. I've got around 8 years of FRC mentoring experience. That's something I did throughout college. I originally started doing FRC as a high school student on Team 1002, the Circuit Runners. And from there, when I went to Georgia Tech, I started mentoring Team 1648. And then finally, throughout my professional career, I decided to stick with Team 1746, Team Auto. Next slide. So today, I'm just going to talk a little bit about the general concept of feedback first, how we can use sensors and data to help us get feedback, and then a couple of common feedback controllers that are implemented in FRC, including the bang bang or on-off controller. And then I'll talk a little bit more in depth about PID, how PID works, and how you can design your own PID controller. And I wanted to end with breaking down our Aimbot software from 2019. For those of you who are familiar with our robot, that year, our robot was designed to drive right into a scoring target only using a camera. So I'll be talking about how we came up with that and how we developed that software. So how do humans know where they are relative to a goal? Say, for example, that you want to become first chair at your instrument or in your, if you want to become first chair for your instrument in your band or orchestra, how do you do that? Well, you want to get feedback, right? You want to receive some constructive criticism from maybe a mentor or from a coach, and you want to be able to accurately critique yourself. You then use that criticism to improve. So as you get better, or when you first start playing an instrument, your instructor will correct your posture and form. And as you get better, you're able to self-critique and make minor adjustments in order to get even better and at your performance. All right. So talking about robots now, how does a robot know where it is relative to a goal? So you may use a couple of points of visual feedback. So an example of this would be like, if my robot is on the field, I may look at where my robot is relative to an element or a position. These are commonly known as sweet spots. So if you have a specific spot that you line up to fire, that is considered visual feedback. You could also just shine a light at the target and look at the size of your light and where it is in relation to the target. That's also an example of visual feedback. You could also do trial and error. This is popular in FLL and VEX. But basically, you time how long it takes your robot to perform some sort of pre-programmed action. And then you just repeat this process, maybe take a mean or a median of all of those time readings, and then just write some code for your robot to perform said action for X amount of time. Another form of feedback, which we're going to be talking about for the most part today, is I'm not sure how to pronounce this properly. Odometric or odometric feedback. It's derived from odometry. But this type of feedback usually comes from like an encoder. So I might have an encoder that gives me a reading on how many times my wheel has rotated. Or I may use a gyro to measure the angle of rotation on a mechanism. So before we dive deep into feedback, in order to get feedback, we need to have sensors on our robot. So some of the common sensors you may run into are switches. These are useful for defining limits of motion. So for example, if you've ever seen a 3D printer or a CNC router run, each of these machines has what are called limit switches, where as you may have guessed, the limits of motion end. So this enables the 3D printer or CNC router to never exceed its physical boundaries, thus causing it to crash or damage its internal components. You might also be familiar with rotary position sensors. So examples of these would be a gyroscope or a rotary encoder. And then lately, what's gotten big in FRC and in robot computing industry in general is image processing as a sensor. So these are like your Limelights, your Javois, your Raspberry Pi co-processors. These all perform some sort of image processing and give you a signal to use in your control systems. So some common sensor setups you might encounter. In your drivetrain, you might use an automation direct encoder, or you might use a Grayhill 63R encoder. These encoders are very popular with the Vex Pro gearboxes. And lately, what's been popular has been the CTRE mag encoder, the cross-the-road electronics mag encoder. These are all great encoder choices for your drivetrain, and they all perform kind of the same function, right? They just allow you to get some sort of information about how many times your drivetrain wheels or axles have rotated. Since we're talking infinite recharge, most of your teams probably built a wheeled launcher. For a wheeled launcher, some examples of sensors could include a CTRE mag encoder, a versaplanetary integrated encoder. So these are encoders that are built right into the versaplanetary gearboxes. These are great because you do not have to design some sort of enclosure for your sensor. And any encoder in general with a high RPM tolerance. Your wheeled launchers are going to be going typically at a faster rate. So you want to make sure your sensor that you're using to track your RPM can handle those sorts of rate, can handle that RPM. So for an arm, other rotary mechanisms, a common setup could be an encoder for measuring the distance that your arm has traveled or the angle that your arm is at, and then a limit switch to make sure that your arm can never or the motor driving your arm can never go into a position that could damage your robot. Limit switches are very useful, again, for defining your range of motion. And then another, it's not really a sensor, but one popular approach, or one approach that's becoming more popular now, is to use current monitoring. So if you look at the relationship between voltage and current, as your robot runs into some sort of resistance to its motion, it's going to draw more and more current. So looking at, if you read your current logs, you can look at where the current is being drawn and where it spikes, and that is a good indicator that you are running into some sort of resistance to your motion. So current monitoring can be used in place of limit switches, for example, if you're trying to limit your mechanism's motion. Can also be used for various other applications like monitoring your drivetrain's performance or monitoring how far your wheeled launcher's RPM dips and how much power it needs to get back up to speed. So I want to talk a little bit about the general idea of feedback. So one caveat, I am not a controls engineer, but I have studied it a little bit in college. So this is going to be primarily applicable to FRC specifically. But in general, we have two types of feedback, open loop and closed loop. So in open loop feedback, you just have your input, your motor controller, and then the output to your motor. There is no mechanisms for adjusting the input. So a time-based movement, or using visual feedback would be an example of an open loop controller. Now, a closed loop controller is one where you do have some sort of mechanism for correcting or adjusting the input. This is where you would use a sensor to indicate or to determine where you are in relation to your goal, and then consequently adjust the input to the motor controller so that it can get to its goal faster. Next slide, please.
Sorry.
No, that's fine. So let's talk a little bit about some of the common feedback controllers that you may run into in FRC, or you may find useful if you haven't used them before. So first, I want to talk about the bang bang, or the on-off controller. So as this controller name on-off implies, you define an endpoint. Say you have a wheeled launcher and you want it to go at 5,000 RPM. When you're not at that endpoint, you're going to want to set that motor to some constant power, so 75%. In your code, you'd write if the motor RPM is not at 5,000, then set the motor to 0.75. And then as soon as you cross over that endpoint, you want to set that motor to a much lower power, maybe like 20% or even 0, hence the on-off or bang-bang. In this controller, you just have 2 power settings for undershooting and overshooting. It's a very, very simple controller. And so if you have a system with a lot of rotational inertia, right, this would be great for those types of systems. It's very simple, and since all you need to do is tune 2 different power settings. So next I'm going to talk about PID and then a little bit of F. So most of you may be familiar with the term PID. It stands for proportional, integral, and derivative with a feed forward. So a PID controller uses what's called an error signal, which, if you're familiar from your science classes, the error is usually defined as the expected value minus the actual value. So a PID does what's called a mathematical transform to generate an adjustment to the input based on this error signal. This allows it to, in essence, race to whatever point it needs to reach. A PID controller is great for applications requiring precision. So if you need to be at 5,000 RPM exactly for your shot, or within a narrow window of that, a PID controller is great for getting you there and keeping you there. It's also great for just drivetrain motion. If you've used any of the motion magic libraries or any of the motion profiling libraries, it'll always ask you to tune PID constants first. But that process of tuning takes a lot of time. So failure to account for that can lead to maybe potentially damaging your mechanisms, or just not that great performance. And tuning is just a very long, drawn-out process in FRC. It takes time. In Otto's experience, the majority of our time on the software team is spent tuning. Writing the actual software doesn't take as long as tuning the software to work in competition in a competition environment. All right, so I think for this next slide, we're going to do some math. I'm going to pull up the whiteboard if I can here.
I'm gonna stop sharing my screen and see if you can then share whiteboard.
Okay.
Okay, give that a shot.
Share whiteboard. Could y'all just post, I guess, quickly in the QA if you can see the whiteboard at all?
We can see it. It says.
Excellent.
Thank you, Akash.
Thank you.
Oh, Sahan too. Confirmed confirmation of visuals.
Excellent. So I'm going to make a few assumptions here. Well, assumptions might be a misnomer. But let's just work through a scenario real quick. Let's say we want our robot to drive 10 feet. Yeah. Let's say we have 6-inch wheels on this robot, and we're using an encoder with 512 pulses per revolution. Actually, let's do 128. I have that worked out already. So if we want our robot to drive 10 feet, oh, this whiteboard, I'm not sure if I like it too much. If we want our robot to drive 10 feet, we first need to find out how many pulses of the encoder it needs to go. So to do that, all we have to do is multiply 10 feet. Well, first 10 times the linear, whoops, never mind. You'd think that being a teacher, you'd be more experienced with talking in front of crowds, but it's weird when there is no actual crowd there.
I'm with you, man.
So let's say we have 6-inch wheels, right? So the linear distance that we would need to drive, or each encoder rotation would give us, oh gosh, this whiteboard is not agreeing with me. So one rotation of a wheel would net us about 6 times pi, 3.14, or 19.2 inches per rotation. If our encoder has 128 pulses per revolution, our encoder should give us 128 times 19.2, whoops. Sorry, 128 divided by 19.2. Pulses per inch. So then we take that quantity, multiply it by 120 for 10 feet, 12 inches per foot, and that would give us the total number of pulses that our robot would need to go. So 128 divided by 19.2 times 120 equals total pulses our robot needs to go. So let's start with when we have to do PID, we have what are called KP, KI, and KD. These are all constants that act on the error signal. Error is defined as expected minus actual. So we're looking at, I'm going to do the math here quickly, 128 times 800. Okay. So when we first start out, our error would be 800. So we need to go 800 pulses. When we first start out, error would be 800 minus 0. So when you're creating a PID controller, the formula for doing so would be KP times error plus the, can I do a triangle here?
Looks like you have some shapes to your left.
Left.
Well, I see it on the left.
Yeah, just a couple of shapes. That's all good. I'll just draw a little triangle. Oh, let's pretend that's a triangle.
And you need to scroll down your whiteboard for us too.
Okay.
Unless I need to scroll down my whiteboard. Oh, it's your whiteboard. Oh, I'm scrolling too. Hopefully everybody can see a triangle.
Yeah. I'm just going to restart the formula here. KP times the error plus, I'm going to call it delta error times KD plus the sum error times KI. So this is our general formula for a PID loop. Each of these KP, KD, and KI are your PID constants. P with the proportional, D with the derivative, and I with the integral. All of these terms act on this error signal, which is just your expected minus your actual. So let's go ahead and go back to the slides, and I'm going to actually show you in software how we implemented these.
All
A lot
right.
of these are already implemented in WPI lib or in the Phoenix libraries.
Okay, are you seeing your slides?
Yes.
Okay. And let's see if we can advance them. Is this showing what you want?
It's showing what I want, although I did say we were going to look at the software implementation, but that's just because it's not in the order that I wanted it, but that's okay.
I can jump.
No, it's fine. Let's keep it at this. So in general, when you start tuning your constants, you want to start with Kp. This is your proportional constant. It acts directly on the error. A kind of technique that I use for tuning was to start really low and then multiply by 2 for undershoot. So undershoot means if you're not able to reach your target. So say if you're trying to drive that 10 feet, your robot never gets to that 10 feet, you want to multiply your KP by 2 first. If you're overshooting, so if your robot drives 15 feet instead of driving 10 feet, you're going to want to divide by 10 at that point to see how that affects. This is a very kind of visual process. And as you get closer, what you're looking for is a consistent oscillation around that set point. So as you get closer to that constant oscillation, you may make minor adjustments to your KP. As soon as you dialed in your KP, and you'll know you've dialed in your KP when you see your robot just constantly oscillating around that endpoint. When you've dialed your KP in, you're going to want to enable KD at 10 times your KP. KD acts on what's called a derivative of the error, which is just saying if I take my error at this point and my error is at my next reading is maybe 10 units higher, then we're just looking at that change in error, which would be 10 at that point. So KD acts on that change in error. And this is just used to bring that oscillation down. So rather than oscillating, this KD constant will actually allow you to get closer and closer to your set point. Again, multiply by 2 for undershoot, divide by 10 for overshoot. And then my third piece of advice is for you to ignore Ki. You probably don't need Ki. If you do need it, you have to be careful with it. You should have a way of resetting the summation of the error to 0. And I highly recommend reading CTRE's documentation on PID for a more mathematical approach. This is just kind of a visual approach to tuning PID. For the more mathematical approach, definitely check out their documentation. So how much time do we have left?
We have about 15 minutes before Q&A, and then we have 15 for Q&A.
Excellent. So I guess a general summary of PID. For your proportional gain, it's going to be something like, let's see how far I am from the target. As I get closer, I will begin to slow down. For your derivative gain, a good summary would be, let's read how far I am from the target. And let's do it again. And then read the change in distance from the target. As this change in distance shrinks, I will begin to slow down. And then a good analogy for your integral gain would be, let's see how far we are from the target. Let's add that to the previous reading. If I couldn't reach the target before, I should be able to get closer now. So that Ki is really useful for if after P and D you just aren't able to get to your target, if you're still undershooting a ton, or undershooting just a little bit, that integral gain would be great for getting you to that set point. All right. So now I want to kind of dive into the case study. So in 2019, let's go to the next slide. Thank you. So in 2019, if you were around, you may have remembered the game Destination Deep Space. This was what's called a pick and place style of game, where you would pick up a game piece from one part of the field and place it in another part of the field to score. So these games require precise placement when scoring. So one thing we kind of brainstormed and thought about was if we can maximize our scoring cycles, we can maximize our scoring cycles if we minimize the time it takes to line up and score. So our end goal for every single mechanical iteration, every single programming iteration, was to minimize the time it takes to line up and score. One key thing was that each scoring location had a vision target. So remember that. So as we got into the software development phase, we set this goal of we want the robot to be able to drive automatically into a target and lined up to score. We broke this down then into 3 requirements. The robot must be able to identify where the scoring target is. The robot must be able to rotate to aim at the target. And the robot must be able to drive into the target. So to accomplish this, we looked at 2 different sensor setups. Our first attempt was to use a Javois camera and custom Python code to write on it. This solution was complex and untimely. I will admit that I ended up looking at a lot of the code and writing some of the code myself, and I was not as big of a fan of doing that versus allowing our programming team members to explore and learn, mainly because they didn't have the necessary skills or the foundational knowledge to be able to use this type of system. So for our second attempt, we used the Limelight. The Limelight I highly recommend. It is expensive, but it's very simple to set up and program. There are in-depth guides available online, and most importantly, it allowed us to build a foundation it allowed us to lay a foundation that we could build up from. Any person new to programming could easily get a Limelight up and running and get the feedback they need from it. So a little bit more on the Limelight. The Limelight gave us XY offsets from a crosshair. This X offset provides data on rotational alignment from the vision target, meaning if our crosshair is centered and our target is appearing to the right of it, we need to rotate towards that direction. And then the Limelight also gives you the area of a bounding box around the target. Now, if you've ever noticed if you stare at a photo, if something's further away, it appears smaller, right? And the closer you get to it, the larger that object appears. So the larger your bounding box area is, the closer you are to your target. And the further away from the target you are, the smaller your bounding box area will be. So we define these target box areas and target X offsets, and we use these to get our error signals for depth and rotation. All right. So in order to design what we called the Aimbot, right, we started with deconstructing Arcade Drive. Arcade Drive can be deconstructed into a drive signal and a steer signal. Drive indicates the power that you go when moving forward, and steer is a signal for how much to rotate in a direction. So these are there are native function calls in WPILib for Arcade Drive. We just went ahead and decided to mathematically redefine them. So you can see that there's a pseudocode over here on the slide where we just mathematically define Arcade Drive as the summation of your drive axis input and the summation of your drive axis and your steer axis. And signage for that may vary based on how your Talon or your speed controllers are set. So now that we've redefined Arcade Drive in terms of a drive signal and a steer signal, we could actually implement the Aimbot. Are you able to click on that video? Is it able to show?
Keep your fingers crossed.
Come on. Yes. It's kind of choppy, but this was a very early implementation of that Aimbot. So you can see it rotates into place and it drives slowly into the target and stops right in front of the target. So you can see kind of in this code here, we pulled this straight from our GitLab. We created these methods to generate a drive command and generate the steer command. So we're looking here at the steer command being generated. So all we're doing is we're first defining an error signal, which is just the X offset from Limelight. We're making sure that it's a unique value so that we're not, making sure it's a unique value. We define our delta error, which is used for our KD. And then here in this else clause, we have the meat of our feedback controller, where we're defining a P and D loop. So you'll notice we have this command, Limelight steer command is equal to TX error times steer KP plus delta TX error times steer KD. And these steer KP and steer KD are constants that we tuned over time. We're finally returning that Limelight steer command. And in our drive code, when we held a certain button down, rather than getting the steer signal from the controller, while that button was held, it would just get the steer signal from this generate steer method. So that was just kind of how we implemented a PID loop and how we designed the Aimbot. So all it was just a very simple way of using a PD loop on using a Limelight to automatically steer us into a target. Now, we never actually used the generated drive command in a competition, only the steer. So the driver still had control of how much power the drivetrain had going forward and backwards, but when they held that button down, that's when the Aimbot took over and automatically steered it into the target. So that's kind of all I have.
I'll stop sharing this, and I think we can maybe go to Q&A if you'd like to.
Yeah.
I don't know if you can see the Q&A, Anupam?
Yes, I can.
Okay, so if you want to take a shot at some of those questions, and others, this is our Q&A time. So if you would like to throw something in the Q&A panel, go for it. And if you want to start with Ava Bird has one in there.
Where can we find this PowerPoint presentation after this meeting? I believe that Georgia First will be hosting all of the, we're recording all the sessions, and Georgia First will also be hosting the PowerPoints for each one. Is that correct?
I believe so. We're fine-tuning as we go. At worst, I think these PowerPoints will be linked right next to where the videos themselves are linked. And we'll get that settled within the next couple of weeks.
All right.
Other questions coming in. There we go.
One issue, so Akash asked, one issue we've had in the past is our robot not necessarily driving straight. Is there a feedback setup that could adjust for this? We tried implementing it with the gyro, but we couldn't really figure it out. So this is one where you can use a gyro and you can use a PID loop for it. You want to make sure that your encoder readings on one side are equivalent to the encoder readings on the other side. So depending on how your robot's set up, you might actually want to use different PID constants for each side of the drivetrain. You might have more weight on one side of a drivetrain over another. You may also have differences in manufacturing that are contributing to one side not necessarily going at the same rate as the other, even with the same signal. Otherwise, you can implement, you can add a gyro error signal. So that would be kind of, I'm blanking on the implementation off the top of my head, but Akash, if you want to email me, I can look through some of our code archives to see how we've implemented that in the past.
Just to slide one thing in there too, for us. First, make sure your robot rolls straight. Mechanical issues can stop straightness a lot. The other thing, Ed Barker from 1311 did write a series of tutorials for some C++ code, which are easily transferable, and he did one on the NavX gyro and how to use some of that and get some of the feedback. But it's close to the same math here that you've seen Anupam lay out in his code. Other questions? Because I got a couple, so nobody's going to line up.
Now, keep in mind, I'm not an expert controls engineer. I'm just a teacher who's had some experience with this.
Yep. So just to ask you the question, you showed this, but just to go back over it, what is your hardware setup? It looked like you were dealing with Talon SRX with a Gray Hill encoder. Is that what you were using for your drive?
Yeah, so for the 2019 robot, we were using the Talon SRXs. We actually never had our encoders plugged in for that robot. All of that Aimbot stuff was all through the Limelight, all through Vision.
Gotcha.
On our 2020 robot, we do have encoders, and I believe we're using we're using Spark Maxes for our drivetrain. And we have these custom Automation Direct encoders, actually, since Automation Direct is one of our major sponsors.
Very nice. And have you guys used a lot of the Motion Magic stuff? For those who are looking to learn more about this, would you recommend pursuing that, or would you recommend pursuing something else for the very beginners in our group?
So for the very beginners, I guess there are some good tutorials out there on the CTRE site. I personally don't have a ton of experience with the Motion Magic or motion profiling. I'm one of those people that likes to do it or write the implementation in our code. But for our newbies, I would maybe look at some of the pre-built PID functions, look at the CTRE guides on how to set that up. A good sensor setup would be like the Talon SRX and the CTRE mag encoders, since those just use breakout board, and those are supported by Crossroad Electronics. And there are guides out there for setting those up and setting up your constants.
Great. Any other questions for those out there? You have one there?
So Akash asks, so do you use the WPI libpid subsystem, or do you manually implement it? For our 2019 Aimbot, we manually implemented it. I don't like to use anything that's black boxed like that, but that's me, just because I like to look at the internal mechanisms and see how it works. For the Talon SRX, though, the 2020 robot, we used a lot of the Talon SRX's internal PID functionality. But I've never used the WPI libpid subsystem library, I guess.
And we have time for a couple more questions.
So Akash asks if for something like a Victor SPX, you'd probably recommend just manually implementing it. And again, this is my personal take. I like to manually implement things just because I can see how the code's running, and I can see where exactly we might have any issues. If you know, or if you have somebody who's experienced using the WPI libpid subsystem, I would say go for it. But if you manually implement it, I feel like you have a better understanding of what's going on behind the scenes with a PID loop and how it's actually generating that signal.
Thanks for the questions, Akash. Anybody else? Okay, and just to remind everybody, these are all being recorded right now. Thank goodness I pressed the record button. And thanks for your patience with us as we're fumbling just to make sure this we get this right for you folks. I've never hosted before, and I think this is Anupam's first presentation today, so thanks for your patience with us.
Yeah.
Any last thoughts, Anupam, before we send them on their way?
Just reiterating, I do appreciate your patience. I'm sure you can tell, I was pretty nervous during this presentation, and the math on the whiteboard didn't exactly work out the way I wanted it to. So I'm going to actually update that when we post the presentation slides, so that it's more easily readable and you can follow along better.
Great. Well, thanks, Anupam, for putting on this presentation. I know PID is a thing that I struggle with still, so I think some of your really simple things like ignoring the I for a while really helped me out, and many other things. So I look forward to seeing these slides with the details. Everybody else, thank you for coming today. Hopefully you have a great rest of the day. And once again, thanks again to Anupam for having a great presentation for us. Folks, see you later.
See you later. Thank you for attending.
I'm going to press stop recording.